This next section is called Quantized Energy and Photons. It is often extremely new to students, and I'll just tell you, this is what I did my PhD thesis on. I was fascinated by the fact that light could cause chemistry to occur. So let's get to it. When you look at something that is hot, the picture of the pot here on the stove, if you touch it, you will get burnt. So definitely there is energy. So imagine back in the old days, a qualitative assessment of heat would be, well, it went to red, it went to white when it became heated, and it became very, very hot. So I also included here the picture in the steel mill. If you've ever been to one, it is incredible how hot it actually is. Well, people then tried to assess this in a quantitative manner. And what they found is that the intensity increases with increasing temperature, and it was proportional to the factor of temperature to the fourth. Now, I took this picture. This is not for our class, but I took it out of a higher level textbook. And what they did is they derived it mathematically, they plotted data, and they found that it actually did match. So that was a good sign about trying to relate temperature and heat energy. Well, when they looked deeper, what happened is what we learned about a classical wave model, it actually failed. Warm objects, they did not give off UV, they did not give off X-rays, they did not give off gamma rays, they simply did not give off energy in that manner. So as people explored a little bit further, Planck in 1900, he proposed that the smallest quantity of energy is a quanta, and it has to be a whole number. Now, this again was very revolutionary. It was like someone saying, the earth is flat or the earth is round. But again, that's where science was at the time. He said that energy was proportional to frequency. He replaced the proportionality with an equal sign and a constant, and he named the constant after himself. It is called Planck's constant. It is always given to you. So before we do a calculation, what really is a quanta? Well, in your mind, think about stairs, that is a quantum. If we were in McPherson 1000, I would be walking up and down the stairs. Instead, I'm sitting in my dining room, okay? Versus a ramp, which is something that we will call continuous. And as we develop the models, we'll use these terms again. But the whole idea is think of stairs as being quanta. Now, light is a wave. That's what we said in the first section. But also, light is a particle. And it is very hard, if this is the first time for you, to accept that that is going on. It is called the photoelectric effect, and it has to do with photons. And it was an observation. When light was shown on a metal surface, the surface emitted electrons. Like, how do they even know that? Well, what they did is first you have this little picture here. It shows radiant energy hitting a metal and how electrons are being generated. Well, they measured it by setting up an apparatus where the top is just what we see in the upper picture, but there was also a current indicator. And again, this is the 1900s. This is all brand new. What they noticed is that every metal had what's called a threshold frequency. You will see that in the homework problems. It will say, what is the frequency necessary for electrons to be emitted? And again, that's what this section is about. So again, when they shone the appropriate light on a metal, they saw current because the electrons were drawn to the positive terminal, and as they had an ability to measure, they did. So along came Einstein. And Einstein, he proposed that this radiant energy, it is a stream, not a seam, it is a stream of photons, okay? And they're like tiny energy packets. And he called them particles. And that's where the concept came that photons behave like particles. So you have the Einstein equation, E is equal to h nu. And that related energy and frequency using Planck's constant. So from that came what is called the wave-particle duality. Light is both a wave, that was section 6.1 where we saw the interference patterns, and it's also a particle because of the existence of the photoelectric effect. So all of this is factual background material, And what do you need? Well, you need to know what had happened to answer a Kant's question. But what you also need to know is how can you do a calculation? And I'll be honest, it is extremely easy, all right? So what we have here is a photon versus a mole of photons. The problems are set up in this manner. It says a laser emits a signal with a wavelength of 351 nanometers. Calculate the energy of one photon. Well, that's the point I need to make first of all. When we use Einstein's equation, it refers to only one photon. We have been given the wavelength, and so what we're going to do is we're going to change that to hc divided by lambda. Constants will always be provided. I wanted to keep the slide as neat as possible, so I'm just placing them in. Planck's constant, 6.63 times 10 to the minus 34 joule seconds. Then we have the speed of light, 3 times 10 to the 8th meters per second, and we divide this by wavelength, which will be 351 nanometers. And what I'm going to do is I'm going to say a meter is 10 to the 9th nanometers. So again, I'm doing everything in one line. That tells me I have 5.67 times 10 to the minus 19 joules. And again, this is only for one photon. So think back. What if we want to do a mole of photons? This is what we taught in chapter 3 about what does a mole really mean. So if we would now try to calculate 5.67 times 10 to the minus 14 joule, that is for a single photon. But what we want is a mole of photons. So we will then multiply by Avogadro's number, 6.02 times 10 to the 23rd photons for every mole of photons. Again, it's using Avogadro's number. We would come up with 2.254 times 10 to the 5th joules, and normally we report it in kilojoules, and it would be 225 kilojoules per mole. I do this calculation because it's the type you most likely will see on a midterm. Midterms go by learning objectives. They may have you do wavelength and frequency, but chances are instead they'll have you do the energy and realize, is it the energy for one mole or is it the energy for one photon?